Hello. In this video, we are going to find the pH of a solution of the diprotic acid, sulfuric acid. The concentration is going to be 0.04 molar. In aqueous solution, sulfuric acid first dissociates to give up one proton plus the hydrogen sulfate ion, which is most commonly called the bisulfate ion. In this particular step, we write it with a single arrow because sulfuric acid is a strong acid, at least for the first proton, so it dissociates completely to give up one proton plus the conjugate base, which is bisulfate. In aqueous solution, bisulfate ion, HSO₄, also has acidic properties, and it gives up one more proton, and the conjugate base for bisulfate is going to be the sulfate ion, SO₄. Now here we are careful to write the equilibrium with two arrows because bisulfate is a weak acid, and the acid dissociation constant is 1.3 times 10 to the minus 2. There is no Ka, there's no acidity constant for sulfuric acid for the first proton because it is a strong acid. We should, when learning, immediately commit to memory the important strong acids because there's not that many of them, and one of the most important is sulfuric acid. Another way to come to the same conclusion is that if you believe an acid to be weak and you look up its acidity constant, its Ka, in a table, and you can't find the acid, that might be a strong indication that the acid is strong because there are no listings for strong acids in Ka tables for weak acids. We notice that, at least to some extent, sulfuric acid is ultimately able to donate 2 protons to the water solvent, which is why we call it a diprotic acid. As a bit of nomenclature, note that the conjugate base of sulfuric acid is the bisulfate ion. Conjugate acids and bases differ only in one H+. Now the conjugate base of bisulfate ion is the sulfate ion. The conjugate acid of sulfate ion is bisulfate, and the conjugate acid of bisulfate ion is sulfuric acid. You actually have all the materials right now, the initial concentration of sulfuric acid and the acidity constant for bisulfate, to calculate the pH of a solution of sulfuric acid that has a concentration of 0.04 molar. So if you like, you can pause the video and attempt the solution yourself, and then turn the video back on when you finish to double check your answer. Welcome back. We notice in the first step, the first ionization of sulfuric acid, since it's a strong acid, that it breaks up completely into one proton and bisulfate ion. So we notice that there's a 1-to-1 correspondence between the number of moles of sulfuric acid and the number of moles of H+ of protons that are added to the solution. So we can immediately write down that the concentration of H+ that came from the first ionization of sulfuric acid. So we're going to write it down this way to be very careful and clear where the various different species come from. So immediately we get that the contribution to the H plus concentration from the sulfuric acid in the first step is 0.04, and we can write this down immediately because sulfuric acid for the first ionization is a strong acid. By the exact same reasoning, we know that the concentration of bisulfate ion, at least the amount of bisulfate ion that is created from the dissociation of sulfuric acid in the first step, also has to be equal to 0.04. So we'll put this down here. And we put clearly H₂SO₄ to show that this is the amount of bisulfate that's generated in the first step. Now that we've handled all the information from the first equilibrium, which essentially goes to completion, we can now erase this particular reaction and we don't have to worry about it anymore. Next, we want to write out the equilibrium constant expression for this second step, and recall that the products go in the numerator, the reactants go in the denominator of the equilibrium constant expression. Now note that these particular concentrations are the total. So this is the total H plus concentration, the total sulfate concentration, and the total bisulfate concentration. So notice I've been very careful that I have not put any subscripts for these particular concentrations. And by the definition of the equilibrium constant, this value has to equal 1.3 times 10 to the minus 2, and to make life easier, we're just going to write that as a decimal as 0.013. Now we notice in our equilibrium constant expression that the concentration of sulfate, it'll be easy in the sense of sulfate only comes from one source. So there's only one source of sulfate, so we're not going to need to do anything with the sulfate concentration. On the other hand, H plus, here's the total H plus. Well, we know that we got some H plus from the initial step, from the undissociated sulfuric acid, and we're also getting H plus from bisulfate. So we have two sources of H plus here. We also have two sources of bisulfate. So bisulfate is formed in the first step. It's formed from the dissociation of sulfuric acid. But we also lose some bisulfate when it dissociates further to make H plus and sulfate ion. So this particular expression is simple in the sense that there's only one source. Here we have two contributions, and here we have also two contributions. So let me write that out explicitly, so that the total concentration of H plus we get from the amount of H plus we got from the sulfuric acid in the first step, plus the amount of H plus that we got from the dissociation of bisulfate. The situation for bisulfate ion is slightly more complicated in the sense that in the first step we have sulfuric acid dissociating and forming bisulfate, so increasing the concentration of sulfate ion. But in the second reaction, we have a decrease in the concentration of the bisulfate ion that's exactly equal to the amount of hydrogen ion that is formed. So for every 1 mole of H plus that's formed in the second step, we lose 1 mole of bisulfate. So these give us the overall changes in the concentration of H plus and in bisulfate, and it is these particular values that need to be substituted into the equilibrium constant expression. Notice again that the sulfate ion only has one source. It's only formed in the second step, so we only have one contribution to its concentration. We notice that both of these expressions have the concentration of hydrogen ion that's caused from the dissociation of bisulfate. So that suggests assigning that as our variable. So we're going to let x equal the concentration of H plus that comes from bisulfate ion. Once we made this assignment, we can substitute our variable x in for these expressions. So we get a plus x for the first expression, and we get a minus x for the second expression. So you have to be very careful with the signs in this type of a calculation. Notice also that we have a value for this expression and for this expression after the first step of the ionization, and we know that each of those is equal to 0.04 molar. So we can express the overall concentration of H plus as 0.04 plus x. We know that the concentration of bisulfate ion that was formed from the dissociation of sulfuric acid at the first step was 0.04. That was easy because sulfuric acid for the first ionization is strong, minus x. So the total concentration of bisulfate ion is equal to 0.04 minus x. Now recall in the second equilibrium, the second step, that when we have dissociation of the bisulfate ion, for each mole of bisulfate ion that dissociates, we get 1 mole of H plus, so that's this expression here. We also get 1 mole of sulfate. It's a 1-to-1 relationship. Therefore, our variable x is also conveniently equal to the concentration of sulfate ion. We get this from the stoichiometry of the second reaction. Now that we've made these assignments and created these expressions, we want to substitute the expression for H plus, 0.04 plus x, into our expression for H plus in the equilibrium constant. We have an expression for sulfate, which is simply x, and we have an expression for the concentration of bisulfate, which is 0.04 minus x. So in the next step, we're going to substitute each of these expressions into the equilibrium constant expression. So substituting in, we get 0.04 plus x, that's our H plus. Our concentration of sulfate is x, and our concentration of bisulfate is 0.04 minus x. So now let's attempt our common trick. And to make life easier, if we could assume x is small relative to 0.04, then we'd be able to omit it from the left and the bottom expressions. So let's assume that x is much smaller than 0.04. So if we do that, that means that 0.04 plus x is basically equal to 0.04. And 0.04 minus x is equal to 0.04. Now when you simply have x, you can't ignore it. So if we do that, that makes the numerator 0.04 times x. So let's kind of just show what that approximately would be equal to. We have 0.04 for the expression in parentheses and we have 0.04. And we know by cancellation that we can cancel the 0.04 on top and bottom. So what would that give us? That would tell us that x is equal to 0.013. But is this very small relative to 0.04? Our test is if it's bigger than 5% of this. So a way to also achieve the same result is if you have your x, multiply it by 20. If that number is bigger than the target value of 0.04, then you're okay. But if we multiply this number by 20, we get 0.2. 0.2 is much, much bigger than 0.04. So, or you can just figure out what 0.013 is as a percentage of 0.04, and you'll see it's more than 25%. So our assumption is bad. We cannot make this assumption in this case. So therefore, we're going to have to use this expression as we've written it to determine the concentrations. So now let's multiply this out, and we get the numerator 0.04 times x plus x squared. And then at the same time, we're going to multiply each side by 0.04 minus x. So that gives us our right-hand side being equal to minus 0.013x plus 0.00052. And then we can rearrange this as a quadratic equation with all the terms on the left-hand side. X squared plus 0.053x minus 0.00052 is equal to 0. So now we have a quadratic equation to solve. In general, solving quadratic equations in math class is not difficult because usually the coefficients are whole numbers or numbers relatively the same size as each other. When we get quadratic equations in analytical chemistry, we very often have numbers that are very, very different in size and that have a lot of decimal places, which makes it more complicated. So here we see that A is equal to 1, B is equal to 0.053, C is equal to minus 0.00052, B squared is equal to 0.002809. There we go. And then for AC is equal to minus 0.00208. And we recall that the solutions for the quadratic equation, values of x are going to be negative b plus or minus the square root of b squared minus 4ac divided by 2 times a. So that gives us that x is equal to minus 0.053 plus or minus the square root of 0.002809 minus 4ac, with minus so it's a plus. 4ac is 0.0208, and we know that a is equal to 1, so divide it by 2. So this gives us minus 0.053 plus or minus the square root of 0.004889, all divided by 2. Taking the square root, that gives us that x is equal to minus 0.053 plus or minus 0.06992, all divided by 2. And this gives us that x is equal to 0.00846. So remind us what this is. This is equal to the concentration of H plus that we got from the dissociation of sulfuric acid, the bisulfate ion. So that's just part of the overall H plus concentration. So we recall that the overall concentration of H plus had two contributions. One of them was the amount of H plus that we got from the initial dissociation of sulfuric acid. And then the second contribution came from the amount that we get from the dissociation of the bisulfate ion. And now we've actually determined each of these contributions separately. So we know from the first step that the amount of H plus we got from the first step was 0.04 molar. We now know from the second step that the amount we got was 0.00846. So this gives us a total hydrogen ion concentration of 0.04846. So now the only thing left to do is to recall that pH is the negative log of the concentration of H plus, the total concentration of H plus. So the pH is going to be the negative log of 0.04846. And once we do that, we get that the pH of this solution is going to be 1.31. I thank you very much for your attention. Have a good one.